So welcome everyone to the session of Functional EDSL for Economics Concepts and Models by Allister Beharry. We are glad that Allister can join us today. Allister will be here answering you in person.
Hi, my name is Allister. I'm going to be talking today about functional EDSL, economic concepts and models. So we only have a short session, so I'm going to try to get through as much as I can. I'm first going to look at just an introduction and demonstration of the Sylvester language, and then I'm going to look at how we can look at different economic concepts and models in Sylvester. Just a bit about me. I've been a .NET programmer for a pretty long time. I'm currently a student at the University of London, and I'm interested in all types of open source mathematical computing tools, libraries, languages, anything that can help me in my math studies. So just a bit about F#. Well, we're all pretty much familiar with F#. It's a functional first .NET language from Microsoft. It's very similar in syntax to OCaml. It runs many different runtime environments. It's used in many different areas, financial programming or web development. And most importantly for us, it contains a lot of features allow it to be used interactively and interoperate with different libraries and tools. So we're looking at how we can use it to interoperate with different tools like Maxima and C3. Okay, so about Sylvester is a F# embedded domain-specific language, mathematical computing and visualization. And the basic idea is to have a single language that can provide a common notation for the different aspects of mathematics, the symbolic, logical, and visual aspects. And basically to have different syntax and types representing these different formulas, properties, operations, and theorems, and also diagrams. Right now, basically with software for mathematical computing, it's kind of split between things like theorem provers, computer algebra systems, and visualization libraries. So the idea of Sylvester is to have a common language and a common notation for these different aspects. And you have these different tools like Maxima, Z3. Maxima is as a computer algebra system. Z3 is an SMT solver. Gambit is a game theory library, and JSX Graph is a graphics library. And these libraries generally, they don't really interoperate that much. So what Sylvester tries to do is to provide a unified syntax and a unified interface to these different open source tools. Okay, so just a bit about embedded domain-specific languages. These languages basically allow you to reuse the host languages, just add some domain-specific elements to that language. So you don't have to invent an entirely new custom language. You can reuse very well supported language and still add these different types and syntaxes for these different domains. And F# particularly supports implemented EDSLs with many different features allowing you to implement EDSLs. One really cool feature is that you can actually compile F# to JavaScript. So we're going to look at later how we can actually use this feature to write a EDSL for doing visualization in F#. Okay, so that's basically why are we using Sylvester? Why not another custom language? Basically, we, as math students, how we study mathematics hasn't really changed that much in hundreds or possibly thousands of years. The way we study math today is pretty much the same of how students, a long time ago did it. And, possibly one reason is that all the different tasks that we need to do in math education, they're kind of split up between these different software libraries like theorem provers and computer algebra systems. So the idea of Sylvester is if you can have one single language that can do all the different aspects of mathematics and math education. Okay, so let's look at the Sylvester language. Okay, so we're gonna just open up our namespace. And we want to initialize the Maxima computer algebra system. So we're going to use that as our basically symbolic computing backend. And we open the real numbers because that's basically what we're going to be using mostly for mathematics and economics right now. Okay, so this is just a simple algebraic expression in Sylvester. Okay, so this is a pretty common expression. And we can use functions like factor, so we can factor this. And then what we can do is, so this is how we can basically use these functional paradigms, like basically like pipelining functions. So we can pass the expression to the factor function, and then take results of that and pass it to a function to do partial fraction expansion. When you do all this, it's in one line in a typical functional fashion. Okay, so that's how we can basically get partial fractions. from our expressions. And well, we have real functions. So this is a function of a real variable. Okay, and we evaluate. So what happens in Sylvester is that in F# we use the ordinary brackets to do function evaluation, but we want to have custom evaluation for mathematical functions. So we overload the square bracket operator to do mathematical function evaluation as well. So this actually gives you back a numeric function. But if you operate on, for example, scalar expressions so if you have like a symbolic constant, operate on that, you get back a symbolic expression. So this is how basically we do sort of like custom function evaluation in Sylvester. And what we can do is we can fix if we have particular constants, we can fix the values at a particular value and evaluate that expression. This has the value as a numeric expression because we fix the value of a at 6. All right, so let's look at just simple calculus. So basically, this is just simple calculus operation on our function. So we can find the derivative, we can integrate. So here again, we're combining operations again in the usual functional way. We're integrating twice, and then we're sending that. We're going to find the limits of the result of that function. Okay, and so here's a function of two variables. And basically, so we just define this much the same way as we define function of one variable. And we can just differentiate this with respect to a variable. And we can also do things like find limits at infinity. So all these are really like common calculus operations that the students would have to use basically during their education that we can do in Sylvester. Okay, so we have trigonometric functions, and we can just quickly go through this. So basically, just regular trigonometric functions, we can find the derivatives, and we can reduce using these trigonometric identities. So basically, all these different operations that we have to do in math education in Sylvester. Now, how we solve equations in Sylvester, basically we have this equation system, and what we do is we use this double equal sign to represent logical equality, in contrast to the equal sign, which gives us basically just the regular F#, how we assign values, but we want a custom operator to denote logical equality. So here's our equation system. Okay, so this is our equation system, and we can solve this basically. Each variable we can solve this. Okay, so we have the symbolic A in our F, so we get back this. So this is fully symbolic, so you're going to get back a symbolic expression. So what you can do is you can say, okay, I want to assign the value 3 to that symbolic variable A, and then solve that system. Okay, so that gives you back a regular numeric expression. Okay, so that was an example of a linear system. We can also solve non-linear systems. So this is like a regular quadratic equation. And we also have a non-linear system where we have a non-linear equation plus a linear equation. So we can solve the maximum as a really powerful equation. So we can solve all these different equation systems. So we get back a numeric expression for that. And we can also do optimization. So we can use Z3, which is an SNT solver, to do optimization. So here we have an objective function. I'm going to maximize this objective function using these constraints. Here we have a custom less than and greater than operator. Okay, so let's maximize this, and well, we get back this solution for that maximization operation. It's a simpler maximization problem. We want to maximize area of a rectangle given these constraints. Okay, so we can do these things pretty easily in Sylvester. So all these different calculus operations we can do in Sylvester. Again, Sylvester has a theorem prover. So basically, this particular theorem, it's actually true axiomatically. Okay, and so we don't actually need a proof of that because that is true basically because of the axiom of distributivity. But this expression needs a proof because this isn't actually true. This isn't true axiomatically. So if we try to do this, basically we get back an exception because the proof isn't complete. So what we need to do is we need a proof of this. So we can just write a simple proof of that, and we can get back. So yeah, that proof that works. So we have a proof of this. So Sylvester can do logical like theorem proving, but we're not going to look at that today. We're going to more focus on like the symbolic and the visual parts of Sylvester. Okay, just a bit about the language internals. Sylvester uses F# quotations for the symbolic expressions. So basically, you can have an expression, you get back a quotation from it, and we use this basically. So when we didn't define our custom operators, we modify the quotation to get a new quotation. So here we have subtraction, so we're modifying it to get back a new quotation. And then we can take these expressions, and we can actually we can generate code for tools like Maxima and Z3. So for instance, if we're solving an equation system, and we can look at the Maxima output. So we translate the equation system from the quotation to the Maxima language. And here's the maximum output as we interact with maximum. So this is basically an example of how Sylvester interacts with these different tools. And just basically that's about the fact that F# is a hybrid functional language. It's really ideal for mathematical computing because many times these objects naturally form hierarchies. Okay, and naturally you want to be able to say, okay, I want to treat this particular object as a set right now, or maybe as a relation. So basically, the idea of interfaces and hierarchies, inheritance, is really natural to math. And that's why F# is a really great language. Plus, you want to retain that functional, having those functional paradigms from math. So that's why F# is a really great language to do this type of math computing software. Okay, so let's look at briefly basically the visualization part of Sylvester. So Sylvester lets you create interactive mathematical visualizations using JSX graph. And basically what happens is that the F# code gets compiled to JavaScript and executes in the user's browser. And you have both a low-level API and a high-level API. So let's look at the low-level API. So this is an example using the low-level Sylvester API for visualization. So if we run this, will actually get compiled to JavaScript and it executes in the user's browser. Okay, and JSX graph has these different widgets you can put on your diagrams where you can interact. So say this is a Riemann sum diagram, and we're just basically just showing how, okay, if we increase the number of rectangles, that's basically what it looked like. So basically this is a way to, JSX graph is a really powerful library for doing mathematical visualization, and we can use this from Sylvester. Okay, so let's talk briefly about a really important part of math for economists which is game theory. And game theory basically models wherever we have rational agents and decision makers, where they interact, where they compete. This is what game theory studies. Okay, and it's a really important field. It's used in biology, economics, business, politics. I mean, basically any sort of field where you have to plan and analyze, where you have intelligent agents interacting and competing. So there are many different types of games, but static games is a really, really common type of game where you have two or more players, and all the players know what the other players can do and what the payoffs are going to be from that action, but they seem to act at the same time, so they don't know what the other players will do. This type of game is a really common, like many different common scenarios. Okay, so let's consider the arms race scenario where you have these two countries, and if both countries choose to spend a lot on military, I mean, it's something that if they choose to spend a low amount, they can have more money for healthcare, education, stuff like that. But if one country does a high level of spending and the other does a low, it means that the other country that spends low could be, invaded by the high spending country. So they'll be at a severe disadvantage. But if they both spend high, it's not as bad as one spend high, one spend low, but still not as good as if they both choose just to not to arm and just to cooperate. So this is a really common scenario, static game example called arms race. And you also have a type of game called a stag hunt, where basically you have two hunters, and the hunters, if it is that they have to cooperate to catch a stag. But if one chooses to defect and say, okay, I'm not going to catch a stag, I'm going to catch a hare, then the hunter that catches the hare would benefit less than if you caught a stag. But if one hunter chooses to hunt a stag and one a hare, only the hunter that hunts the hare will actually benefit. The stag hunter will go up hungry. So this is an example of a really common type of game. So in all these games, you have different elements. You have players, you have actions, you have action profiles. Like, okay, like defect is when both hunters choose not to get the stag and instead choose to go for the hare. You have preferences, so each hunter would prefer if they both had a piece of a stag to take home, and then you can assign a function that represents these preferences. Okay, and you can represent this game in what's called normal, which is a matrix form. So we can look at how we can represent this game in Sylvester. So here's this is what this game is called prisoner term, just like how our arms race was. This is the most common type of static two-player game, and we can represent this pretty easily in matrix form in Sylvester. Okay, so that's basically our game. These are our payouts, right? And this is our stag hunt. There's another type of game called stag hunt that we can represent. Okay, so this particular game, this is called a zero-sum game. And what happens in this game, no matter basically for any player, the sum of what the payouts would be for that particular outcome is 0. So we only need basically the payouts just for one player to represent a zero-sum game. So in this zero-sum game, basically, so we can see for any particular profile, once one player gets a value, the other player gets the negative value. So it all adds up, it all sums to this. This is a type of zero-sum game. Okay, and the basic solution idea is that you have what's called a Nash equilibrium. And the thing about Nash equilibrium is that because you can't enforce cooperation, I mean, it's what's rational for the players to do. But the Nash equilibrium doesn't have to be optimal, meaning that there are other outcomes that would benefit the players more, like how we saw in the stag hunt. But because they can't cooperate, the rational thing for them is basically just to choose the one where they would not be disadvantaged if other players defect. Okay, and so we have this Nash equilibrium, and basically there's a very famous theorem that says basically every game has a Nash equilibrium as a particular kind of strategy profile. Okay, so let's see how we can solve these things using Sylvester. So if we solve the process of the game, we get back, it has one Nash equilibrium. This is the defect defect. This is the rational choice for both players. And the stag hunt actually has two, so it's rational to both of them to cooperate and to defect. Now, the rock, paper, scissors game doesn't have any pure strategy Nash equilibriums, but it does have a mixed strategy Nash equilibrium, where basically each player plays one strategy one turn at a time. So this is a mixed strategy Nash solution. So this is basically how we can solve these different types of games in Sylvester. Okay, so let's quickly try to go through just economic concepts in Sylvester. Okay, so economics studies how a society, how banks, countries, consumers, firms, how they use scarce resources and how they decide what they're going to do. Okay, so you have these different concepts, supply, demand, but economics requires really extensive use of manipulation of algebraic expressions, like all the things we saw, equation solving, constraint solving, and visualization. If you're an economics student, you're going to be sick of having to draw graphs by the time you finish. So we can use the features of Sylvester to see how we can actually work with these concepts. Okay, so let's look at, first of all, let's talk about our production. Just a production function is just basically a function that says, okay, how does a firm take inputs like labor and capital and produce items from this? Typically, it's a two-variable function. And you have these different measures like marginal product of labor, which is just the first derivative, then average product, which is just the function over the variable L. So we can basically see, so let's open our Sylvester economics module, and we can define our this QP is a production function here. So we're using the different types from Sylvester to define a production function. Okay, and what we can is we can fix that particular k bar variable. We can fix that at 10. And what we get back is a function of a single variable now. Okay, and we can calculate stuff. Okay, calculate the marginal product of labor. So this is just, we're actually like differentiating basically with respect to L. And the average product, we're just dividing. So this is how basically you calculate these sort of measures in Sylvester. Okay, now this is an example of the high-level API in Sylvester. So this is the graph we actually showed on our title slide. So we're using a very high-level API to draw this, and we just have basically certain properties and saying how we want to visualize this. Okay, so this is basically how we can use. So I can set this to a simple example. If I want to draw a red screen, I can set it like that. So this is a really simple example of how we do visualization. Okay, and so here's another production function. And what we can do is we can actually fix this and get a new function. And then we can draw what we call isochords. Oh, okay. So this is okay, so that's what we've read. So let's just go to our cost functions. Okay, so in addition to production functions, we have cost functions, right? So cost functions basically say if a firm is producing a quantity of goods, what is going to be cost to the firm? So you can actually break from these costs into fixed costs and variable costs. And then you can measure things like, just like how we saw we have a marginal product, we can measure things like the marginal cost and the average cost. Okay, so let's just define a cost function here. Okay, and then so we can evaluate. So what we can do is if we evaluate the function where it's 0, we can actually find what the fixed. So that's basically this cost. It's just what it would cost the firm to make, even though we're not making any good. This is like the fixed. It's like, just the fixed cost of or whatever it is that we're producing. Okay, and we can calculate stuff like the marginal cost. And so what we can do is, again, we're going to use a high-level API here. Sorry about it. Yeah. Okay, that's good. Yeah, we have to be careful about that syntax. But this is the high-level visualization API. So basically, so this is we're drawing two graphs. And this is our cost function, this is our marginal cost function. Okay, and so we're observing how basically as we increase in quantities, basically the costs go up. All right, so that's basically an example of how we can use these different economic concepts. So the last thing we're going to look at is how we could use just economic models. Okay, so economic models basically model these different scenarios given certain assumptions. I mean, it's the common thing is that all economic models are wrong. Some of them are useful. And economic models that generally require a lot of manipulation, constraint solving, like how we saw before. So what we can do is we can combine capabilities that we saw before from Sylvester, into these different types that represent these models. Okay, so let's look at how we can do this. Okay, so let's look at this really simple model called consumer preference. Okay, so the three consumer preference models, they just analyze how consumers choose goods to purchase and the price they're willing to pay. Okay, so basically the main assumption is that you have a utility function that says, okay, I'm going to get, if I have two goods, this is the utility I'm going to get from these goods. And consumers have this budget constraint that says, okay, I only have this money to spend on buying these two goods. So I can only spend a certain amount of money on the two goods. And then what you can do is from these, you can find a demand function that tells you, okay, how much of these goods would a consumer be willing to buy at a particular price, given their utility function and given the prices of the goods and that. Okay, so here's how we define this purpose model in Sylvester. We see we have a type of economic model that we inherit from. And basically, we just define the different variables. We define the constraints using the same expression language that we saw before. Okay, so let's look at creating a model. So we're going to create an economic preference model. And what we're going to do is we're going to use this is what's called a Cobb-Douglas utility function. So this is a particular type of utility function. So we're going to put that as a utility model. So when we do that, so this is the model that we get back basically. We're using this Cobb-Douglas utility function. Okay, and these are the constraints now that we have on our model. Okay, the MRS is just a measure. Basically, what it says is how much are you willing to trade one good for the other. That's what the measure, the MRS actually says. Okay, so this is just a measure. These are different measures that we can use in our model. And what we can do is we can solve the model equations now. We can solve this equation and we can get like the demand function. So when we solve the equation, we actually get these are basically the solutions to the demand function. And when we could put all this logic that we have, all the logic of solving with a different constraint, we can put that into a property of our model. So here we have this. So basically we have this here. So that's basically the idea of having an economic model. All the symbolic and stuff that you want to use, you just put them into the model and the user can just access that without having to go through all the work of deriving it. Okay, and so we're just going to look at visualization. So when we want to visualize a model, we use, again, using the high-level API, we're just setting properties, basically saying, okay, so here we want to see, what we want to see is, we want to look at what are called indifference curves. Okay, so we set the different properties. We set our income as Y, as between 400 and 1500, and we set our prices. We set our utility levels in this range. So we're going to draw this. Okay, so here we're drawing the diagram for our model. So we can see basically, so the curves in red are in what I call indifference curves in this case. So basically, any package on this line has the same utility, right? And the blue line is our budget constraint. So what happens is that as we increase it, so basically any bundle of goods that's below the utility, we know we can buy because it's below, because anything that's above this, it means that we don't have the budget to buy those things. Okay, so this is just a simple example of how you can use Sylvester to create and look at models in economics. Okay, and I mean, rather than doing it by hand, I mean, it is a lot easier to do this than having to draw this stuff by hand. Okay, so what we've seen so far, we've seen Sylvester is an F-sharp EDSL for doing mathematical computing, the different aspects of mathematical computing, and we can use Sylvester to represent these different mathematical objects and concepts, and we can create models, we can find solutions, draw diagrams, automate all different people that we have when studying these topics. Okay, so for more information, you can check out the Sylvester repo on GitHub. You can also check out Gambit Sharp. That's the library for doing game theory. And you can also check me on Twitter. Okay, so it was really good talking to all of you all today. So thanks for having me.
Thank you, Allister, for such a wonderful session. It was too informative. And yeah, if anyone has any queries, we can quickly take.
I should say sorry about the rooster crowing. We have a lot of animals, so sorry about
Was it happening live or was it? I was
that. It was
confused.
no, it was in the video. This was like early in the morning, so of course the rooster has to start up. So sorry about
Okay. So thank you, Alistair, for such a wonderful information sharing. We can go back to Hangout and connect in person if anyone has any queries and doubts. Thank you for joining.